Hello.
Hello, Kyle. How's it going?
Hi. Yes. Can you hear me okay?
Yeah, I can hear you. Miguel, I'm gonna be chairing your session today.
Okay.
Nice. Yeah, we're gonna wait maybe a couple of minutes or so that more people can join.
Sure.
Um, could you try sharing your screen and so on just to check that everything works
Yeah,
fine?
sounds good. We
Cool.
put this in presenter mode. Hold on.
Perfect. Thank you.
Presenter view. Okay. Sharing it? Let's see here. Oh, not yet. System settings. I'll have to quit and reopen. 1 second.
Yeah, no worries.
Okay, I just had to update a permissions thing, so this should work now.
Okay.
Okay. I think you guys can see it
Yeah,
correctly now.
yeah, nice. Yeah,
Fantastic.
perfect. So, yeah, I guess we can start then. So, we have Kyle Cahill. He's going to be talking about cognitive resource theory. Uh, yeah, so feel free to start.
Okay. All right. Hello, everyone. My name is Kyle Cahill. I actually began my studies intending to become a medical doctor. Then, after taking a modern physics course with a theoretical particle physicist by the professor Diego Castano, I found a new calling in physics. That experience sparked a lasting fascination with fundamental principles that underlie complex systems and subjective experience, which eventually led me into the field of neurophysics. During my PhD at Georgia State University in the States, under my supportive advisor, Dr. Mukesh Tamala, I developed as part of my dissertation what I call cognitive resource theory, which models cognition as a thermodynamic and gauge-theoretic process of energy allocation and reallocation of the brain. Earlier this year at OHBM in Brisbane, after Michael Breakspear reviewed my work, he agreed that my ideas seemed to align with the free energy principle. And then later on during the conference, I had the pleasure of running into Polly Toussaint, hopefully I pronounced that correctly, who from McGill University, who I discussed my work with her, and she was just absolutely lovely and encouraged me to reach out to Carl directly, who has kindly connected me with the theoretical neurobiology group today. And I'm grateful to everyone here for facilitating this opportunity to share my work and ideas. I'll begin by basically giving some background and motivation behind this framework, and then walk through the formal construction, and then discuss how this connects with the free energy principle and where I see this work going next. Okay. Checking. All right, good. So first, empirical overview and motivation. In our lab, we previously found that action video game players, gamers, can make faster video motor decisions with slightly improved accuracy compared to non-gamers, overcoming traditional speed versus accuracy trade-offs. My work expanded on this project, looking at structural and functional connectivity differences in the brain associated with this effect, And I looked at both a deep analysis of the dorsal and ventral streams, now published in Brain Sciences, and 2 other papers that followed up, which are currently under review and should be are due to be published pretty soon, actually, where I looked at whole brain analysis using both a tractography constrained functional connectivity approach and a method that I came up with that leverages the patterns in participant covariability, which I call RCPCA. That's outside of this particular talk, but it's a new method that I came up with that kind of allows for data-driven reduction, allowing you to streamline whole brain analysis especially in small sample sizes, smallish sample sizes like we had here. So to go into a little bit of detail, that action video games themselves are very complex environments that are graphically rich, they're fast-paced, they're challenging, and they require quick visual processing, demand quick decisions, and require many hours of play to improve. In this kind of environment, the task is not simply just pressing a button on a screen to screen flashes. From the perspective of the person playing these games, it's engaged in a recreational activity such as including tracking fast-moving targets, managing risk, coordinating timing, and adapting strategy. Success depends on how quickly and precisely the brain of the person playing these games can predict and select and execute contextually appropriate action. Okay, so the study itself consisted of 47 participants. Groups were age-matched college students. We had standard recruitment criteria. If you're a gamer, you played 5 hours a week or more. One of the 4 types of video game genres that we classified as a action video game, including first-person shooters, real-time strategy, multi-online battle arenas, and battle royales. Non-gamers averaged about less than 30 minutes of any video game playing per week over the last 2 years, and all passed the HRO color blindness test. The primary hypothesis that we had for this framework here was that under repeated conditions, such as a sustained cognitive engagement or high cognitive load evoked by these fast-paced environments, that the brain would basically reallocate a finite amount of its resources to reinforce task-relevant circuits. This would lead to things like improvements in task performance through neuroplastic refinement that reflects reduction in visual motor surprise, defined here as the unexpected visual or motor information during decision making, through superior mechanisms of resolving visual motor uncertainty compared to non-gamers. The mechanism proposed, which I came up with, was cognitive resource reallocation, which is a mechanism that would describe how these changes might occur. An idea that the brain dynamically reallocates its resources when task demands strain baseline support. Over time, this regulation would upregulate task-relevant circuits and downregulate redundant or inefficient ones, leading to functional optimization, which supports more proficient task performance. And this idea is not exactly new in of itself, and has support in the neuroscience and neuroplasticity literature, as we'll see further, but none have really formalized it from the perspective of fundamental physics, as we'll see momentarily. Basically, just walking us through what a vision motor decision is in this context with respect to the task that we have. We have a modified moving dots task where you have a cued color and you have the direction, and you have to make a choice if the dot's moving left or right relative to a different color of dots moving the opposite direction. And then this maps to the decision-making sub-processes, including sensation, accumulation of sensory evidence, some sort of motion perception, mapping to some sort of action, and then you going doing that thing and taking an action, all modulated by attention, selection, and control. The task itself was based, again, I mentioned, is a modified moving dots task to measure the vision motor decision making. Each trial began with a 2-second cue. For example, green, telling participants which dot of colors to pay attention to. After the cue, 2 sets of dots, about 600 each, appeared on the screen, moving in opposite directions, but only one matched the cued color. The instructions are incredibly simple. Be as accurate as you can, be as quick as you can, and you have 3 seconds to respond. The task timing, it was assigned a difficulty level and speed setting based on the standard color wheel here. The blocks consisted of 15 seconds of task followed by 15 seconds of rest. Directions and colors were randomized each time with respect to task difficulty for the block. And to vary the task difficulty, as I mentioned, we use this the color pairing from the standard color wheel with them. And we also included various speed settings as well. This task is pretty low level and it's very easy to understand with minimal explanation to remove any potential bias that gamers might have in doing this task. And I'm gonna kind of play you guys a very short clip of what this task looks like, so you guys can decide, see what it's like for your to kind of do this thing very quickly. This is on the hard difficulty setting, so see if you can get it. Great. So that's just an example of what the task will look like for the participants undergoing this experiment here. We collected, let me go back here. Okay, we collected this data using a Siemens 3 Tesla MRI located at the Center for Advanced Brain Imaging in Atlanta, Georgia. We collected T1, we collected fMRI while participants were doing the task with a TR of about half a second, a little bit more. And then the brain diffusion, and we also collected DTI data as well for each participant. Getting into the methodology of what I did with this data, first we did pre-processing. The diffusion data was pre-processed using DSI Studio, and then after this we did motion correction, eddy current corrections, all that good stuff. But on the fMRI side, using tools from like AFDI and FSL, following like the Enigma pipeline provided by a lab colleague, Beam Adikiri, a PhD graduate of the Damala lab, helped us with the providing the pre-processing scripts that we leverage for this work. The product that we used, again, I'm going to go over this very briefly, just kind of highlight, again, general trends in our results, and you'll see this pattern pop up over again in these results. On the left, we have a target analysis of the dorsal stream, and then a dorsal ventral stream, and on the right, we have a whole brain analysis. So I want to point you to this pattern. Where gamers are higher, you see this negative correlation, meaning with association with reduced response times, the higher the metric. So wherever we see gamers were higher, we also saw this pattern in the brain behavior data. For example, in this connection between the left superior occipital to the left superior parietal, which was our significant result here, which was Holm-Bonferroni corrected. We see, again, gamers are higher in the measure, and then this negative slope here. Alternatively, whenever we saw gamers were higher, or non-gamers were higher, we see this positive correlation. So the higher the metric, the slower the response time in that brain region. And these are kind of very much in task relevant areas. Here we see like temporal, for example, this guy indicates a strategy more towards detailed visual object recognition before committing to a decision. Whereas in the parahippocampus, for example, this connection here on the second one, we see basically this idea that, but we're seeing that the parahippocampus, which is crucial for spatial scene processing, and the superior temporal pole, which is known as a conversion hub of high-level sensory information, we suggest that gamers seem to be better able to process scene-specific and contextual information, such as for processing, for example, the relative motion between dots, than individual comparisons that the non-gamers seem to make, as indicated by the results of this data. Now, again, we continue to see this pattern in graph-theoretic analysis. Again, wherever gamers are higher, negative correlation. Wherever non-gamers are higher, positive correlation. And it just propped up over and over again throughout every mode of analysis that we looked at, that I looked at. And I went through a lot of them. Like I went through functional connectivity, directed connectivity, structural connectivity, and even coupling, structural functional coupling. The upshot is this. As a summary across these studies, we see converging evidence that repeated engagement with high demand vision motor tasks, such as action video games, leads to neuroplastic refinement characterized by top-down prioritization of salient and feed-forward goal-directed action selection, bottom-up motor readiness for a rapid, efficient execution and real-time error correction, enhanced processing of task-relevant visual information, and greater cognitive flexibility and intentional control. Moving from this, that's the CRR as an underlying hypothesis that might explain this. Again, this is a cross-sectional design. However, I would point out that I observed zero contradiction in my results that could even begin to go against this mechanism as a possible explanation for what we're seeing in our data. And so the convergence of this, I mean, I just came out of basically, rigorous, brutal graduate level physics classes. So I'm like, well, I know some physics now. So let's see how this might look if I try to formalize this thing as a real physical process instead of just a nice conceptual heuristic. Because if this was a real thing that might be going on, it would be useful or especially informative to understand what might be actually happening in the brain. So this led me to constructing what I call cognitive resource theory as a way to formalize this mechanism. Okay, I'm going to take a sip of water because we're going to get into some interesting math here in a sec. Okay. Before we begin, there are some conceptual preliminaries that are super important to discuss here, just so everyone has some sort of baseline understanding of what we're going to be talking about for the next remainder of this talk. We have this idea called a Lagrangian, which is a path scoring function in something called state space. In typical non-relativistic systems is just the difference of kinetic and potential energy. Integrating this Lagrangian over time defines a quantity that we call the action, which is a realized path, or also called a history, which is one and typically is stationary under small variations. The Hamiltonian is a function of a system's input-output energy flows in phase space that determines how the system will evolve in time. In typical non-relativistic systems is the sum of the kinetic and potential energy terms. These distinct but mathematically equivalent descriptions of the systems are linked together through what's a transform that's called the Legendre transform. It's just a formalism that was able to link these things through mathematical machinery. Now, like any good theory, we have to start with some postulates, some underlying assumptions about the thing that we're just trying to describe. Here, we describe it's a cognition, or a cognitive system is a dynamic physical system that evolves in time. Because it's a physical system that evolves in time, I can describe it by a time-dependent Hamiltonian, and I posit that it'll take this kind of form. And we'll get into the specifics of why I think this is a good choice among all the possible things that we could have chosen. As a physical system, the cognition obeys the principle of stationary action. Like any other physical system, it evolves a path that tends to minimize or extremize its action over time. And then cognition as a physical system also obeys the second law of thermodynamics, which states that the entropy of a thermally insulated system cannot decrease and is constant if and only if all processes are reversible. So in a closed, real process that you don't see this usually this reversibility, and that the entropy tends to increase. So I'm going to walk us now through this construction of this Hamiltonian, and walk us through the different parts and what they're each describing. Here on the allocation side, we have a dynamic equilibrium influenced by factors such as metabolism, homeostasis, and internal resting state. This would reflect the brain's baseline and time-varying cognitive resources available to perform cognitive tasks modulated by the nervous system. This resource allocation concept is established in biology and neuroscience and cognitive psychology literature already. On the reallocation side, we could describe it as a first-order perturbation by which energy is dynamically redistributed when task demands strain CRA baseline. This reflects the system's energetic investment to resolve misalignments between allocated resources and external demands, up-regulating effective circuits while down-regulating ineffective ones. This concept, again, is supported by neuroscience and neuroplasticity literature, but none have formalized it from the perspective of fundamental physics. Under this model, we can basically think of what we saw earlier, this improved functional connection between the left superior occipital to left superior parietal, analogous to muscle training. This also is aligned with Dr. Nancy Canwisher's ideas about functional specialization and these kinds of ideas. The idea that demand for rapid visual processing in the case of actual video game playing induces some sort of cognitive strain analogous to muscular fatigue. The brain would then reallocate energy to facilitate signal propagation between these areas more effectively. And over time, repeated cycles of strain and refinement would then lead to noticeable behavioral adaptation and cognitive improvement in the context of video game playing, meaning that like you, in terms of very layman speak, you begin to be less bad at playing that video game. Despite there might be people being better than you just naturally, you can, the whole idea, like if, hard work beats talent when talent doesn't work, that this kind of idea. So moving in now to the mechanics of the theory. So the cognitive resources reallocation itself is modeled as a dynamic equilibrium that's relatively stable, and is modeled as a conserved field over over space. It's described by again, that's a negative gradient of a scalar potential. This parallels formalism in electrostatics and fluid potential flow. That kind of formalism. Then we also have a vector potential that governs the dynamic flow of cognitive energy over time and across regions. And then from this, we can construct a cognitive field tensor for the system. We pick a Lorentz gauge because Lorentz gauges are typically used in time-dependent electromagnetic fields. And so this would yield the Lagrangian density function as shown here, and from which then we can just find a Lagrangian for the system. Okay. So that kind of gives us our baseline, our understanding of how we would describe this how cognitive resource allocation under this theory. On the reallocation side, we have this first order perturbation term, and we have it modeled as as an epsilon term, where it gives us our units of energy as our perturbation coefficient, times what's the reallocation function, which is the negative gradient of the free energy of the CRR component over the energy available for reallocation. The energy available for reallocation is taken as the total energy that the cognitive system has, subtracted from the energy that's used by CRA, subtracted from the energy that's used by, let's say, the system itself to maintain things like homeostasis, and that's locked by the body. Now, this term here, we'll get into why we see this term here, but we might be able to recognize it as a gradient descent of the free energy with respect to the available energy for reallocation. If you see here, when you take a nice little integral from 0 to the energy that's available, we see that basically we can have a measure for the total energetic reallocation investment, which would correspond to the amount of available, the energy that's available for neuroplastic adaptation. Epsilon here would be a quasi-static perturbation coefficient with units quantifying the energetic gain under CRR. Possible candidates I've come up with would be proportional to basically the second derivative, where basically this would describe a stiffness or curvature, which would allow us to, because it's under where K has units of 1 over energy. When you take, by simple math, this would allow you to recover the units of energy that you would need to describe a proper Hamiltonian or perturbation term. And possible candidates would be, if you want to describe it using the energy that's available and the total energy, you would describe it using the formalism on the left here. Or if you wanted just everything in terms of the energy that's available, then you can probably find a similar form just using the energy that's available. So these are just possible candidates I've come up with as what you would use for epsilon here. So one thing to do is we want to make sure that our theory is consistent across Lagrangian and Hamiltonian formalisms under this theory. To do that, we're gonna apply the Lagrangian transform and set the effective mass equal to 1 to simplify the kinetic term. And so when we start, we see clearly that if you go through the logic of this, I'm going to leave this for a moment, that you clearly can arrive at a Lagrangian for the system that is coherent and consistent with what we had, meaning that basically that the reallocation function can be recast under Hamiltonian or Lagrangian formalisms, which validates its appearance in the Hamiltonian Jacobi equation, which is basically the classical analog of the more famous or more well-known Schrodinger equation. So another thing to do here next would be looking at predictive validity of the theory. Now, Here I'm showing that basically that CRT can make concrete predictions about brain energetics across sleep and wake states. Here we basically have the Hamiltonian and CRT, which splits into a baseline cost, the CRA, and the dynamic reallocation, the CRR. CRR is again defined as a gradient of the free energy of CRR with respect to the available pool, which is simply the total brain energy minus the energy that is locked. Yes. Minus the CRA. Yeah. So it's described by the energy, the total energy subtracted from ECRA minus the energy that's locked. When we integrate R across the available energy, we get a simple result that basically the reallocation energy is the negative change of CRR free energy, which is the same idea that underlies work done by a system under core thermodynamics. Importantly, this is as the pool of available energy grows, the CRR entropy would grow with it, increasing the total energy for reallocation, which is why when that CRT predicts that the lower cognitive baseline load under sleep, under non-REM sleep specifically, would free up or predicted to free up more available energy for plasticity. And then when we, so if the baseline CRA is higher during wake than it is during sleep, then the available energy is larger during sleep. So this is the prediction here, that basically that there's more energy for reallocation during non-REM sleep or sleep than wake. Okay, well, in under empirical studies that I looked into this, that basically non-REM sleep is known to decrease to approximately 85% of the waking value, energy to 85% of its waking value. The non-REM sleep state has also been associated with enhanced neuroplasticity relative to wakefulness, which aligns with the theory's prediction that a great amount of energy should be available for CRR for CRR reconfiguration during sleep as opposed to wake. Now, the next part of this thing to go into is the thermodynamics of the system, of this theory, under this theory. So to define the total free energy, we begin by examining the free energy expressions under two core components, the allocation and reallocation. We're going to look at the center here that defines the baseline energetic configuration. Unlike CRA, which defines the relatively stable baseline, CRR governs the adaptive response to cognitive strain. Because this reallocation departs from the baseline established by CRA, the thermodynamic contribution can't just be subsumed under CRA's free energy. Instead, CRR warrants its own free energy profile to capture the distinct trade-off between investing internally available energy and overcoming configurational entropy. The energy available denotes the pool, again, the pool of cognitive energy accessible for reallocation by CRR. It excludes energy already committed to baseline CRA operations, and as well as energy locked by essential maintenance functions, such as, again, homeostasis is a big one that comes to mind, and support of vital systems and other neural processes that are categorically distinct from cognition. On the left, we have temperature. So at, how am I doing on time? Okay, I'm doing okay. At any moment, we can treat the system as a locally stationary, so the partial derivative can be well defined. This framing allows a physiological local brain temperature. We basically have good, well-established literature showing that there's local fluctuations in brain temperature. There's the Keaton 2019 study and the Wayne 2014 study. So this idea of an instantaneous temperature is physically plausible and supported. Entropy here, we're going to get into entropy in detail in a little bit. So for now, I'm going to leave that as the von Neumann entropy of CRT is just defined this way, that you have the density matrix for CRT, and so you can define the entropy this way. We're going to get into the specifics of what the form would look like in again a couple of slides. So I'm going to leave that for now. And then looking on the right, we have something called the neuroplastic, that I've described as a neuroplastic potential, just a very simple measure of the basically as a net change of free energy resulting from energy reallocation. If this potential is greater than zero, might correspond to things like constructive plasticity, such as um, um, long-term potentiation, integration, upregulation, these kinds of things. Whereas if it was less than zero, it might correspond to destructive plasticity, such as downregulation or synaptic pruning. We have an idea for a cognitive efficiency index, where basically we have the energy ratio of the task of the task to be performed, and then versus the energy that's available for energy for cognitive allocation, and then basically whether or not the task is under-supported or over-supported by the current allocation. Here we can actually describe more carefully what each task is. Again, further down the line, you can carefully describe what that would look like. So give me a few moments of your time, a little bit of patience to describe what that might be in further detail as we get into, I guess, more like, in further detail in a few slides from now. This also kind of parallels broader ideas in dynamic optimization, including control theory, attractor dynamics, where systems can configure themselves or reconfigure themselves in response to optimize performance under changing conditions. And there's good literature to support that as well. Moving forward, this I want to get into how it is that we can realize the reallocation function takes a certain form, or why it makes sense to take a certain form. If we want the reallocation to proceed towards a meaningful equilibrium with respect to CRA, so we require the system to evolve that the reallocation function tends to zero, saturating the system capacity for configurational reordering. This requires that the energy minimization for the reallocation process, it requires the minimization of the free energy of the reallocation process, which is recognized as in the community as a gradient descent. So the only way this function tends to zero is if this quantity here, this derivative, tends to zero. But when you take the derivative, you realize very quickly that from the dimensional analysis that all of these are positive definite quantities with fixed units. And because that the CRR elements formed a subsystem within the cognitive resource theory as a whole, the system as a whole, exchanging energy with other constituents, the thermodynamic behavior must satisfy a constraint as shown here, which it means that the expression that satisfies the minimization criteria would be the negative gradient of the free energy of the reallocation function with respect to the energy that's available for reallocation, and arriving at a final expression for what the reallocation function might be. Now, moving into the partition, we can move now into further detail about the thermodynamics, including partition function and entropy. What's really nice is that this cognitive system would occupy states probabilistically, like any other physical system. So you would describe the thing, because the thing is made of atoms at the atomic level or the molecular level, you can use a Boltzmann distribution just fine. And then you can then, from here, describe what's called a partition function, which is like how energy is literally partitioned across your states. And because the system is set up that it's the addition of the CRA plus the CRR parts of the Hamiltonian, you arrive at a very nice clean expression for how the partition function should look. And then now we get into the entropy, right? So now that we have a partition function, the next step is to be able to move into describing what the density matrix for the system might look like. So there's two possible options that are formulated here to present this. One's a very minimal computationally straightforward model, which is, I think, those are mathematically simple as a two paramagnet system. It's a fully separable system. The second is more expressive, where CRA remains like a paramagnet, and CRR is modeled using an Ising-like interaction term to account for real world understanding of things that the brain does, including coupling and synchrony between cognitive units. So under this model, again, under the two paramagnet, we have the expression, we start with the energy. And then from here, we can, where basically we have your SI, which is your spin states, whether they're energetically active or inactive. From here, you can then describe a density matrix. And then using an Ising-like model, you could introduce coupling between the terms this way, and then from here would be able to arrive at a density matrix under an Ising-like model for the entropy. Where if when spin states are aligned, it contributes a negative term which lowers the energy, which what you would expect for when things are more synchronous. It tends to things to flow along more efficiently, so therefore it would conceivably lower the energy. So that's how the formalism is described, or how it's formulated here in this kind of way, where when they're anti-aligned, the pair would raise the energy in this kind of way. So from here, we move into the last part, which basically, and then before tying this all into the FEP, well, the last thing to do is we can consider a path integral formulation of the theory. To capture this, we can look at the path integral over cognitive histories described by generalized coordinates, describing the degrees of freedom, incorporating the CRA and CRR into the total action. We can adopt the convention of natural units by setting the Planck constant to unity here. And then this would allow us to describe a partition function under path integral formalism as such, where S here is the action of the system in this case. And so this would allow us to calculate expectation values of observables through basically as pass through this space. And you can compute things like expected energetic cost or some trajectory or some cognitive process, reflecting things like task difficulty or neural efficiency in executing some task. You can look at connectivity measures. You can look at things like neg entropy using this formalism conceivably to run your calculation. Now, as an example for say expected energetic cost, you can write like an energetic functional in the following with this following form, and then the expression would then follow as such as shown here, which would yield an expectation value for the energy, which would quantify the average cost of the system, what it spend over all feasible cognitive paths when engaging with a given task or decision. Now, bridging this with FEP, okay. The inference model that Carl came up with uses variational free energy as expressed as the log measure of model evidence minus the Shannon entropy of recognition density. And if I'm wrong about any of this, please feel free to correct me, but I think I have the right of it here. So in the high resource limit, basically under CRT at least, the neural population states can become formally separable. In which case the von Neumann entropy in CRT would approach a diagonal form, recovering the Shannon entropy used in FEP. Belief updating is now recognized as having a thermodynamic cost under in Field's paper. Now in 2024 paper, I think together that these frameworks are complementary and they offer together a richer perspective of cognitive adaptation, unifying active inference and physical resource dynamics within a broader framework of physically grounded cognitive function. So however, how this might further interface with FEP remains to me an exciting topic for further investigation. To me, like that interfacing CRT with FEP adds hard resource limits and physical constraints, whereas FEP adds a generative model and inference, and together they lead towards testable resource aware inference dynamics. With Isamura's paper, which showed empirical validation for FEP in the in vitro study, which showed that the neural activity and plasticity evolved around a cost surface consistent with variational free energy minimization, demonstrating inference as a product of self-organized dynamics. I think that this provides a rich opportunity for CRT-based reinterpretation to further interface or to further describe how CRT and FEP can talk to each other. I think synaptic plasticity and firing threshold changes observed. Yes, and that's exactly what I said here. I think which would again provide, I think, a clear bridge between CRT and FEP. And just comparing the two together here in this little table, from the perspective of ontology, FEP looks at cognition as a Bayesian inference or active inference, describing what a cognitive system does to make optimal inferences under uncertainty. It has generative models based on again, the mechanism is through generative models based on active inference. It utilizes Shannon entropy of recognition density, and as an agent-centric framework where the brain minimizes surprise by updating internal generative models, which is uses like I think in my mind, a first-person inference perspective. Answers how cognitive agents make inferences and navigate their subjective experience. Cognition under CRT, cognition is treated from the ground up as a physical system. What a cognitive system can do under a physical constraint. Utilizes energy allocation and reallocation based on physical observables. Utilizes von Neumann entropy and over density matrices, and takes the perspective of a neutral observer that's commonly taken in physics, where you have describing energetic flows in neural structures that support processes that we would call cognition from a third-person perspective, and would answer questions about how cognition can exist at all and operate as a real physical system. I guess it's just a repeat of a slide before. This is basically for terms of future directions. I have here, sorry for the cutoff on this table. Just so because I think I'm trying to model a real physics, use physics. So if that's the case, then I would throw everything at it. I would throw everything at it to try to nail down some of these free parameters and come towards a identifiable human model. Use simulation and inversions, try to validate and falsify, make predictions using just various modalities with their different temporal and spatial resolutions, which each of these can bring to the table their unique perspectives, and can also can bring measures to further validate and test this theory, and as well as also under this theory be able to maybe guide or help inform different modalities, and if shown within certain levels of uncertainty, if those can be established clearly, because any good physics theory has limits of uncertainty. So once if those can be clearly established, then this could actually be used to guide and inform empirical studies going forward potentially. Furthermore, I think in terms of future directions, things like an operator formalism for the theory, which I have thought about and kind of made motions toward. Like a lot of these things I've come to future directions I've kind of already started on or have already done already. It's a brand new theory, so it's going to take some time for things to get off the ground. But things like the operator formalism will give us granularity of states, which allow it to treat cognitive resources as discrete quanta rather than smooth fields, which would add further precision. Would provide a compact algebra for reallocation, as well as stochastic embedding and further FEP bridging. Furthermore, you can think about generalizations of this theory, which I have. This whole framework is generalizable to the whole nervous system, honestly, encompassing all measurable synaptic, glial, and neuromodulatory interactions. And why do I think this is true? Is because I think what this is really about, this kind of formalism that I've happened to think about or just construct here, is a theory that describes the physics that might govern complexity itself, in the sense that systems that are capable of reorganization over time and emerging across scales. This kind of theoretical framework provides the machinery to think about these things in a physically plausible and coherent manner. Thinking about things about internal energy reallocation and reallocation among a system's constituent elements. Now, in summary, we have cognitive resource theory is a theory that unifies physical energetics, neural architecture, and cognition during a single framework. From this perspective, cognition functions as a variational system constrained by thermodynamic costs, aligning with a physically plausible, which aligns with and I think provides a physically plausible extension of the free energy principle. CRT models cognition as adaptive process through cognitive resource allocation and reallocation. And then these describe a resource constrained manifold, which evolves as a function of environmental pressure and internal resource availability. CRT then would formalize this using principles from using gauge theory, statistical mechanics, and dynamical systems together through theoretical consistency and empirical plausibility observed as through long-term action video game experience and sleep-wake cycles. I think established this as a viable theory of cognition as a physically embodied system. And of course, further empirical testing and physiological grounding is definitely required. And I'm only one person, and so I definitely need collaboration and help to move this forward. I would like to acknowledge my advisor, Mukesh Damala, who has been incredibly supportive throughout this whole thing, in helping to review my work, as well as other physicists under my committee who helped review this theory, make sure everything was physically coherent and consistent. Of course, my collaborators and colleagues who have helped in my research, including also, of course, family, friends, and mentors, and the TNB community that's allowed me to present this work to you all. And I hope you enjoyed this presentation. I'm looking forward to your feedback. Thank you very much.
Thank you so much, Kyle, for the presentation. Lots of stuff in there, but really interesting, really interesting. So now we move to the Q&A session, comments. So if there are any questions or comments, please raise your hand and feel free.
You want me to go back to a slide or something? Please, I know I'm perfectly happy to do that. I'm not sure how to go back to screen share or whatever, but yeah.
Yeah. I have like a very general question, because some of the math that you were presenting at the beginning, I'm not super familiar, but when you say that this cognitive resource theory is adding this kind of thermodynamical constraints into, I'm just wondering, so the thought I have right now is, if you move away from the canonical Bayesian kind of representation into a more information theoretic constraint scenario, such as like rate distortion theory or information bottleneck, are you familiar with those?
I mean, you can surmise what they might be just based on your description.
Yeah, so it's just like taking like a sort of a
that's what's cool about math, is like whenever you describe something mathematically, it's like usually it is what it says, you know.
Yeah, so taking like a Gibbs posterior, so basically you have like a weighting between prior likelihood,
Right.
let's say, so you are like performing under constraints. And so my point is that sometimes this weighting is characterized as a sort of how costly is to move your beliefs from one state to another. So how costly is to update your beliefs in that scenario, and that's usually under the bounded rationality literature, or like inferring under constraints kind of literature. So I was just wondering what could be the relation between your theory
like
and
belief updating
the
itself and in this theory, that your question?
Yeah, so basically if you take how the cost of belief update as a Cahill divergence between your belief in time t
Sure.
and updating towards a belief in time plus n, then if you
Sure.
take that Cahill as a cost, like how does that relate to your
So under
theory,
this
for
theory, what you
instance?
could do, you can theoretically calculate the energy it takes you as a cognitive system to perform XYZ cognitive task, and over time, if you get better at doing that task, will correspond to requiring less energy to perform that task. And then you can probably use that to map between variational free energy and the free energy principle, or the information theoretic approach. I think I mean, just top of my head, that's what I would imagine to be so. Does that make sense?
Okay. Yeah. Okay. But let me maybe think a bit more, but I think Takuya has a question there.
Yeah. Thank you, Karen, for interesting talk. Can you hear my voice?
Yes, I hear you.
Oh, yeah. Okay, great. So I have several questions. Yeah. For example, um, I missed the definition of your density matrix in your talk. So how did you define that?
Oh yeah, let me go to that slide, because that's very important.
Yes, thank you. It's very helpful.
Yeah, so that way we can just look at the math rather than me having to like try to explain. You know, it's way easier just look at it. Oh, let me go ahead. No, I went too far. Okay. One more. There we go. That's how.
That's the one.
So you
So
could either take, if you take it as a paramagnetic model on a two paramagnetic, you just like, because the density matrix is described as uh has a canonical form regarding the e to the negative beta Hamilton. It has a formal construction in physics that takes this kind of form. So what you would do is describe what your Hamiltonian looks like, and from there, once you know your Hamiltonian looks like, and you know what your partition function looks like, and the partition function we can get it from here, then you can then construct your density matrix from that. And this is under a two parametric model. I think honestly, this is probably might be computationally easier, but I think the Ising-like model is probably closer to actual reality.
so what is the original state space? So you may consider either continuous state space or discrete state space, right? But
Right. So in you're basically, so here's the idea. The idea is you wanted to figure out what the entropy of the system looks like. So the two concepts that really map between microscopic to macroscopic in physics is energy and entropy. The conceptual, like if you want to go between scales, energy and entropy are usually your links to do that. So the trick here is to how to calculate a clear way of describing the entropy of the system. And to do that correctly, you have to invoke statistical mechanics, which we have done here. So that way you could describe the thing, you can just have a description for the entropy in some sort of semi-classical or classical way. However, I would say that this whole formalism lends itself quite naturally to being quantized and taking on an operator form. It's actually moving between classical to quantization is a very standard, pretty easy way to do that. You just go through canonical quantization. There's it's like like a cookbook to do it. You have to find the main thing is to define your commutation relations and figure it out from there.
okay, maybe I understand or a little bit
Yeah,
figure out
like
what
later
your
on, like
meanings. Yeah,
actually,
yeah.
under the very general terms, you could actually think about things like hold on, let me get this part. Sorry. Things like, oh, I don't have that as a note here. There's like Lindblad equation, like the
Yes, yes.
yeah, that
Limbaugh.
would be something I would point to.
Okay. Yeah, maybe I understand. So that easing model is expressed in a classical form, maybe, but yeah, it
Yeah,
is
the
easy to
reason, right?
quantize.
So this stuff is cast into a classical form on purpose. It does, because you want a starting point, but you get to be
Yeah,
able to talk about things in a coherent manner. I
yeah.
think, but this is completely, I think, honestly, pretty lends itself to operator formalism
Mm, mm,
quite naturally. And I mentioned that I think this is a definite future direction for this kind of thing, is to
yes,
cast this thing in terms of operator formalism, because it gives you so much.
right. So may I ask one last short question about the definition of you defined free energy F as the distant difference between E and TS, right?
Where the
Uh, some something close
well,
to the
well, this is
definition
the
of
this is FEP in
ah
Helmholtz, like Helmholtz free energy is just the internal energy minus the product of the temperature by the entropy.
yeah, I'm interested in exactly that part because to my knowledge this is the thermal equilibrium free energy I mean in a conventional I mean in a standard textbook situation, it is thermal equilibrium state. So it's not a function of t, but you extend that concept to the time function of time, right?
Right. You literally just because you're describing basically a dynamic equilibrium as your baseline, then everything kind of has some sort of time dependence to it, right? At least in some sort of slow fluctuations, at least.
Okay, so you assume the quasi equilibrium state.
Right.
You consider slow dynamics.
The allocation is slow relative would be slow relative to the reallocation, right? I guess
I
is the
see,
idea.
I see. That makes sense. Thank you. Thank you very much.
Sure.
Cool.
Uh,
Thank you for
any
the
other questions?
question. Yeah, let's see. Um, I guess if there are no more questions, maybe you can move to you, Carl.
Is it my turn now?
It
I think
seems
so.
so.
Very good. Thank you. Thank you very much for that presentation. Um, yeah, lots of things to talk about. And I'm impressed that Takua is still awake. I imagine he's in his pajamas, which is why he didn't put his camera on. Right. So before I start asking questions and trying to summarize, I just want to get an idea of how we can help. Um, I didn't realize until the end that you were supervised by Mukesh. That's very nice. Where is he at the moment?
He's at Georgia State.
Oh, right. Okay, excellent. Okay. Is that in Florida or where's
He's
that?
in Atlanta, Georgia.
Oh, okay, right. Okay, so it's not quite Florida. Good. Um, so yeah, I just want to get an idea of what you want to do and where you want to take this in terms of your career structure. So you were a medic. No, you weren't a medic. You're a physics student.
Yeah, I
You're
have a pre-med degree, but I pivoted into physics proper.
right. So at the moment, have you just completed the PhD? Is that where you're at?
Yes, I defended in April, and I'm now graduated. And now right now I'm in the midst of talks of trying to align a postdoc at the NIH, but things are difficult because of things.
Because of
So
Trump or
sure, yeah, exactly. Yeah, I kind of want to be like, you know what
uh,
I mean?
we all have difficulties because of Trump. Don't worry about that. Okay, so you're looking for a postdoc, and at the
Right.
NIH, who were you hoping to work with? What sort of focus were you?
Um, I've actually made contact with a section chief there, Tanya. I hope to basically utilize. I mean, amongst of helping her with a project that she has in mind, the utilize the resources there to do things like I can probably utilize a lot of that data that they have to like look at see how I can use that to inform CRT based modeling and simulation to try to see if I can nail down some of these free parameters and try to get towards more what would this look like in an actual human being and from a neurotypical state. And then because Tanya's work does a lot of neurodevelopmental stuff, including also neurodivergent things, neurodivergent cases, you can then begin to think about how this model might be changed or altered under these kind of conditions.
Okay, excellent. So this is very much translational applied to a neurodevelopmental, possibly autistic spectrum kind of clinical cohort.
I think so. I mean, I think in terms of the potential for applications concerned, it's hard to say how far reaching this could be applied to or where the limits are. And so it's just because it's so new, I think. Yeah.
Yes, no, I'm asking just in terms of, where you need to expose yourself in terms of work. So, yeah, one of the reasons for asking is the kind of audience that you would want to write for in building your CV to ensure that you have the best chance of getting your favorite postdoc, under the assumption that Trump confounds your attempts to get the NIH postdoc. And that was interesting you made that answer because you could have said, no, I want to go and work in a neurophilosophy, philosophy of science, or I may want to go and
Yeah.
work in a company developing thermodynamic computing, or you could have said, I want to go and work with.
I believe that science is usually at its best when there's back and forth between data and theory. I think so. My mindset is okay. If I have a theory, my thought process is okay. Well, time to try to see if I can apply it, see how well it can do in terms of predicting and modeling, and see how it can be implemented in the world. So my stance is like, I mean, physics as a science is born out of natural philosophy, and I love doing philosophy. I love thinking about math and physics. I can do it all day. It's the best. I can just do it forever. But in terms of like where I think what I think makes advancements in terms of moving the ball forward and maybe trying to maybe do a little good in the world and help out people, is if this can be used and to inform like future treatments or future ideas or whatever, what have you, then I would like to see this I would like to see back and forth between data and theory, because I think honestly, in my opinion, physics has gone a little bit astray in terms of just theoretical abstraction to the point of almost beyond the capacity to begin to think about testing empirically. So that's where my head's at, I think.
Okay, well, no, that's very useful to know. Um, from my perspective, knowing what's going on internationally and where you might actually apply these theoretical ideas, I think what you're talking about is probably computational psychiatry or neurology. So harnessing the enthusiasm for formalizing decision making and choice behavior and development and neurodevelopment under these formal treatments. And then, exactly as you say, using this formalism to try and phenotype people in terms of fitting the right rate constants, temperatures, parameters of these formal models to best explain a particular person's behavior in the spirit of precision medicine, or to phenotype various cohorts, say people with severe autism, or people with addiction, or people with depression, or indeed people with Parkinson's disease. So that means you need to, I think, position yourself with that in mind, which would not be trying to develop these ideas for a philosophy audience or a physics audience, but specifically for an applied physics in the context of, in this instance, I repeat, probably psychiatry, which means that's the community you need to expose yourself to and engage with. And I'm saying this very practically because you're at a very early stage of your career. You've clearly got some great ideas. You have a fairly unique background in terms of your physics education, but you are very young and you don't know what you don't know, and people don't know what you know. So you're going to have to spend the next few years um, exposing yourself and being exposed to the community, which is going to, if you like, provide the apt home for the kind of work you want to do and the kind of contributions you want to make. And that would, I think, entail, first of all, looking at the attendees and the themes in the computational psychiatry workshop. So there are two every year. One is always in the same place, and that's in, you don't have to remember this. This is being recorded, I hope. Is it?
Yeah, I think so.
Yeah. Oh, good. It, there's one which is held in Zurich every year, under the auspices of the Translational Computational Neuroscience Unit, run by Klaus Eno Stefan. And the other one moves around the world, usually organized by Rick Adams at UCL in the UK, and by Chowzi Gu, I think is at Mount Sinai in New York. The reason I'm suggesting that is that you will meet people you need to know and would want to know, and people who you should want to know you at these meetings, and get a sense of the various formalisms that are being brought to the table to do this kind of translational application that you want to pursue, over
Right,
the
because
next few years.
I think on the philosophical grounds and those kinds of aspects, I think those eventually can get filled in themselves, or people can take this work and begin to have do philosophical discussion about it on their own. I think where I can be most helpful is in guiding the implementation, as you're saying.
Yeah, sorry, the computational psychiatry workshops are not philosophy. They are exactly what you want to do. I would imagine at some point your potential supervisor at NIH would want to be involved at that level of formalism. This is not the philosophy, this is the applied
Right.
physics of belief updating and decision making of people. And particularly of patients. So it's not philosophy, it is actually um,
Right.
the practical application domain that you're looking at. I would have given you other conferences if you're interested in the philosophy, but you're
I
not.
mean, I'm interested in all kinds of things, so
Yeah,
I like to have my hand in different jars.
that's great, but you also have to, if you like, tailor the way you tell your story so it makes a difference in the area that you want to make a difference in. And
Mm.
that all, and it may sound horrible, but that will also entail making sure that you get funding to do what you want to do. So basically finding the right kind of postdoc that will enable you, give you the space to do what you want to do. The other venues um, are obviously the Active Inference Institute. So you should contact them and see if there are any other um, like-minded um, in theoreticians there who may have a reading group. They may even have ongoing projects which you might feel you can contribute to or can possibly learn from. And then finally, the International Active Inference Workshop would be an obvious place that you should aim to submit. Were you at this year's meeting in Montreal?
No, I was not in this year's meeting in Montreal. I also just in terms of thinking about like taking this work and putting it into a paper, like where to publish these things, like finding collaborators, that kind of stuff. Like you said, in terms of being young in my career, that's completely accurate. And navigating these kinds of things is something that I need to, I'm trying to take slow, but also I want to make sure, I want to put my mark on the world at the same time.
Yes, no, that's exactly why I'm asking these questions. Trying to find the most efficient way of putting your mark on the world. So I noticed that's the second or third time you've mentioned looking for collaborations. That everybody is doing their own thing. No one is going to take time away from what they're committed to collaborate with you just because you're there.
That makes sense.
You have to get an academic position where your supervisor will endorse and encourage collaborative initiatives that are motivated because you've got a good position, a good postdoc working for somebody who has some gravity. So you have to get your badge of honor by getting your postdoc, by locating yourself in a group that has some gravity so that you will attract collaborations. And of course, just by having a supervisor, you will also have somebody to write for and to co-author with. So that's why it's so important to get the right postdoc. Um, you can't do this just by reaching out for collaborators. No one's going to collaborate with you.
Absolutely. That's a fair point. That's a fair point. I guess what the real question we'll be asking here is like formalizing the paper that you wrote when you went to write your paper on FEP. Um, what maybe I might to learn from you honestly, like what you went through to when you what the things that you were doing to form that paper, and how basically the idea is when I go to put this into a paper as a as a thing to be published in the community, like how to go, I guess questions about how to go about that.
Yeah. Well, and in part, that's why I'm asking you these questions, to try and think about the appropriate ways of doing that and the appropriate journals. So, things that immediately come to mind are things like physics of life reviews or the specialist literature such as computational psychiatry. And I think Rick Adams, who was the organizer of the second International Computational Psychiatry Workshop, I think he's the editor or one editor in chief of um, computational psychiatry. So that would be the applied version. And I suspect they'd be quite eager to at least review, if not publish the kind of work the kind of work you are doing. Um, Before I forget, there is another avenue that you might want to just make sure you keep your eye on. So at the moment, we're focusing on application of these formal ideas to, I repeat, what's sometimes called computational phenotyping, understanding mechanistically this person or these kinds of people through the lens of the physics of self-organization and belief updating, however parameterized. There is another growing interest, though, in the thermodynamics of computation or thermodynamic computation. So just keep your eyes open for possibly computer science postdocs, but more likely in industry at some point in your career, where the idea here would not to be to apply it in a medical context or a psychiatric context, but in the context of a move to computation of a substrate dependent or mortal type, using the thermodynamics of chips at the Planck scale to do computations, which has the offer of being much, much more thermodynamically efficient and therefore sustainable than current implementations of inference and belief updating and self-organization on von Neumann architectures. So I haven't got any papers or websites, but there are companies out there, usually startups, who are particularly interested in understanding the thermodynamics of computation, because if you understand that, you can actually use thermodynamics to do computation. A little bit in the spirit of quantum computation that Takua was motivating in the context of implementation on a quantum computer. But we're not talking about quantum computing here. We're talking about things like memristors or using silicon chips that are deliberately noisy and harnessing the noise and their temperature as part of the computation. So I'm just saying there is a field out there which is applied computer science effectively, a branch of applied physics, in which there could be lots of money invested over the next decade that is trying to leverage a first principles account of computation from a purely thermodynamic point of view. So I'm just saying that that's there as well. But at the moment, I'm going to focus more on the computational psychiatry aspect, because certainly if you're going to NIH, that's going to be much more relevant for you, and I think easier for you to get an academic position, which you will need before you can go into or which you should have before you go into go into industry. So yeah, so physics of life reviews and that genre of abstract papers that provide overviews of the kind that you aspire to, that join the dots and bring things together, or applied sort of perspective or hypothesis pieces applied to a particular problem, which is phenotyping, understanding the mechanisms of patients. If you wanted to go for physics of life reviews and that kind of publication, it's highly unlikely you're going to be able to sell your PhD thesis at your age. What you can do, though, is draw links with something that is established, which is the free energy principle. So in answer to your question, how did I do it? I spent 3 to 4 decades doing basic research in physics, MRI physics, statistics of imaging, and psychiatry, and qualified as a psychiatrist before starting to write theoretical papers. So I already had a standing in the field. I had my badge of honor in order to do that. You clearly are too impatient to wait for 10 to 10 years or more before you write it. So what you can do is you can leverage people like me. So what you do is I am now going to unpack for you cognitive resource reallocation theory through the lens of the free energy principle, and then draw the parallels, draw the dots, and see how it extends, generalizes, or translates into another field, stuff which is already in the literature that now acquires a new rhetoric and possibly a new parameterization, or at least a new interpretation that may have translational or pragmatic interest. That's what you'd have to do for a physics of life review. You can't go in there as
Right. That would be something I actually would be interested in doing. Like I think I thought about physics of life reviews before, and I think that is the avenue where I would like to publish this theory in that kind of journal. And your input and guidance and how and given your stature in the field would be honestly irreplaceable in trying to get something like that published.
Yeah, you wouldn't need to do that sort of, if you like, riding off the free energy principle for something like computational psychiatry. You could just, say that this is internally consistent at one level
Right,
with the free energy principle, but this is what practically it could offer, and then you'd have a worked example of how you actually apply this
right,
in characterizing or phenotyping, say, addictive behavior or some kind of false inference or failure to allocate failure of resource reallocation and how this might be manifest in certain attention deficit hyperactivity disorders, for example. So there are, depending upon where you're writing, there are different things. In terms of me helping you, I'm too old to be your supervisor, but certainly you can come back to this meeting as many times as you need before you submit your journal. At the point of submission, then you let somebody like me know, and then I it suggests me as a reviewer. So that would be the mechanics of getting support and supervision from somebody like me. I can't be your supervisor because I'm too old and there are too many bright young
sure.
things.
I mean more like once I have a paper drafted, ready to go I mean not like as a what do you, as I call it, like a reviewing author or one of the one on the paper or something like that. Would that be something that you would be open to?
Well, it's an interesting point. We're spending a lot of time talking about sort of meta science and strategy. Usually, I would recommend one of two things. You can certainly do like that. You can sort of send it to me, and I will go through it and make constructive comments. That it takes a long time for me to do that, and I'm having to say no more and more because I just don't have the bandwidth to. There are lots of people writing about things that are related to the free energy principle or active inference, so I just don't have the time to do it for everybody. Um, the the alternative would be not to send it to me, but you have written it after a number of discussions of the kind that we're having now, and then suggest me as a preferred reviewer. That means I don't have a conflict of interest, and then I can accept, and then I can give you a constructive, friendly review. That would be the alternative, which when I'm pressured, is usually the one I prefer. Um, the ideal thing though would be for you to partner with your putative supervisor and co-author it with her or him, or find somebody of your age that you can co-author, knock each other's corners off. That's another thing you should consider. It is very ambitious, and I would say actually dangerous to try single author papers in this field,
Sure.
especially I now simply refuse to even review single author papers if it's an independent researcher. There are too many people in the world writing their theory of everything as a single
Right.
author, especially since the advent of large language models. I receive at least two theoretical treatments a day. And editors are likewise in this position. So just be very careful when you choose your co-authors. Ideally, it would be either your past supervisors or your potential future supervisors, with or without somebody else that you could engage through meeting them at conferences like the computational psychiatry or the active inference international active inference workshop. That I mean, it will slow you down, but I don't think that's necessarily a bad thing. There's no one else doing what you're doing at the moment. There's no one who's going to beat you to it. So you
Right.
just
Yeah.
you just take your time and do it as in a crafted and scholarly way as you can. That's going to have the highest impact. And certainly people like me will help you, but that help will be more in terms of guidance and and peer review as opposed to direct supervision. Um, the One of the purposes of this meeting is to just suggest to you various bits of literature and perspectives that will help you provide a more rounded um, portrayal of the CRR, for example. Um, and so uh, part of the mission of this TMB group is just to sort of point out bits of literature which you
Sure.
probably have come across, but may not have emphasized in terms of joining the dots and building bridges. And usually leverage in the form of lending your arguments a construct validity, by which I mean these are valid arguments in the sense that they have a face validity because they are predicated on physics, but they also have a construct validity in the sense that they also have validity in relation to other constructs. So, for example, for formulations of degeneracy and redundancy in genomics or in cognitive neuroscience. So I'm just going to go through a few papers that I think you should briefly revisit or read if you haven't already read them, just to join the dots so that you can, in one sentence or perhaps even without a sentence, just reference various bodies of work so that people feel reassured and indeed can pursue the paper trail should they be interested, reassured that what you are saying is entirely internally consistent with other constructs and other things. And that will render your paper more publishable, more acceptable via peer review for a physics of life kind of publication. It may not be necessary for a computational psychiatry or you know, or a biological psychiatry submission, which is much more sort of focused. But for a physics of life review, as it says on the tin, if it's a review, you have to be selling an idea um, in the light of other approaches that you will implicitly review in selling your particular idea.
Got it. I see.
So, if you'll indulge me, I'll just quickly go through I've got about 8 little papers that will all remind me to say something. There are lots more that I could have picked up on because as because as you covered an enormous amount of material, right from sort of functional connectivity and structure function correlates in decision making with neuroimaging, right through to density matrices in quantum computing. But there are a number of things that that sort of did catch my attention, which I will be interested to hear after you've thought about it and read the paper in question. Whether this would be a useful adjunct or perspective on some of the things that you brought to the table. Part of the fact you brought a lot to the table. Um, I'll feedback immediately. There are lots of moving parts and lots of different kinds of energies and entropies and the like. It may be that you need to slightly simplify and pick out the sort of the key bits for a publication. You may feel that every little part of this is completely justified and I need to have all of these quantities in play in order to make any useful contribution. I'm putting it to you that it might be a little bit over-engineered. There may be ways of sort of using a portion of the quantities you brought to the table to do the heavy lifting of in terms of what it means to reallocate a resource and what the mechanisms might be and how that could be associated with this and that. And I'll try and give you an indication of how how I would expect to see that expressed when going through these papers. But before I do that, I'll just give you one example and just make a generic point which speaks to your exchange with Takua. A lot of what you talk about seems predicated on quasi-equilibrium statistical mechanics. And yet you want to make it clear that these ideas generalize to non-equilibrium physics and self-organization because the more general problem of the more general problem you're facing is understanding the thermodynamics of self-organization of systems that are open systems, which means by definition their steady states are non-equilibrium steady states. So you just want to make it clear to the physicist reader that you're not talking about equilibrium steady states. And that and that is, if you like, something which may nuance who you are referencing. So you want to make sure that anything you say generalizes from equilibrium steady states to non-equilibrium steady states that are apt to describe systems that are open to the world, about which we are, well, with which we are exchanging, on which we are acting, and from which we get sensory information. I'll just give you one example of that. You can't use the second law, but you can use the Jasinski equality, for example, because the Jasinski equality generalizes to open systems under certain adiabatic. So just be careful when you're going through, certainly for the physicists, that you're making sure that everything generalizes to open systems. Um, so the Jasinski equality. And you didn't actually specifically mention it, but when one does discretize to the simplest, basically the universe can be on or off, or in a up or down spin. Then the quantal change in information and the energy required to erase that information reaches its lower limit, which was basically Boltzmann's constant times log of 50% or 2 minus 2. That's the Landauer limit. Now, the Landauer limit is an important concept to bring into play when talking, as you did, about the thermodynamic costs of belief updating, or at least in conversation in the Q&A session. So, but that may I repeat that well, if you want to make that notion of the maximum efficiency thermodynamic cost of belief updating work in the service or apply to open systems, then you have to move to the Jasinski equality. And the Jasinski equality is itself an example of an integral fluctuation theorem, which provides, if you like, you sort of a generalization of things like the second law. In turn, that also allows you to distinguish between statistical mechanics and stochastic mechanics. Are you aware of the distinction between the two?
Yeah, I think so.
Good. Yeah, because by predicating all your arguments on statistical thermodynamics, you're sort of making an ensemble assumption, a canonical microensemble, or some kind of ensemble exchangeability assumption, which you don't really need to make. If you stick with stochastic mechanics, namely the thermodynamics or applying integral fluctuation or fluctuation dissipation theorems to the path of a single particle, you can now treat that single particle as a person. Whereas if you are assuming statistical thermodynamics, you're making all sorts of additional assumptions that there exists an ensemble of exchangeable particles. So just little things like that might be useful in terms of framing the physics, the kind of physics you're talking about. Certainly when you're starting to talk about thermodynamic. And I should say, when you talked about a physical extension of the free energy principle, I read that as a thermodynamic reading of the free energy principle.
Right.
The free energy principle is actually pre-physics. It starts from random dynamical systems from which you can derive stochastic and statistical thermodynamics, from which you can derive. So that's not true. The free energy principle is derived from the same starting point as quantum mechanics, statistical mechanics, stochastic mechanics, and classical mechanics. So you don't necessarily need to talk about thermodynamics to talk about the free energy principle, but it's nice because they're both predicated or inherit from the same formalism, which is just a random dynamical system in its classical. So I think the job of bridge building between CRR or a thermodynamic description of sense making and decision making and the free energy principle is a nice job. And at least from a classical perspective, is easily done by the fact you both can be derived from the same equations, and those equations are just the density dynamics that attend random dynamical systems. And you even mentioned Schrodinger equations, master equations. So the solution to these density dynamics um, is, if you like, the where the free energy principle comes from. So the free energy principle is not something you guess or intuit. You derive it as the solution to the Fokker-Planck equation, the time-independent Schrodinger wave equation, or the master equation, whatever you're working in. When you derive that solution, which entails steady state under a Markov blanket, that then you get the free energy principle. So your job is to join the dots between random dynamical systems of a generic sort, the free energy principle, and thermodynamic computing by by this vicarious link. And I think that could be done. That'd be really interesting to do that. Well, yeah, I've been wittering on for a little bit. Let me just grab the screen. So yeah, I wasn't going to show this, but I think I will. If you haven't read this, I think you'd enjoy reading this because it has everything in it that I've just said. And in particular, the ways in which you can derive the thermodynamics that you were talking about from first principles without having to refer to textbook physics. It's all emergent. And things like temperature end up being basically just measures of the random fluctuations in a random dynamical system. And what falls out of that is a stochastic thermodynamics, and what one aspect of that master integral fluctuation theorems, of which one example is the Gininsky equality, which you will need later to say that this is the most efficient way of doing it. Just open brackets for your interest. If you find yourself in later life wanting to make a lot of money by working for a company trying to build thermodynamic computers in artificial intelligence or AGI research, then the big move is to break something called the von Neumann bottleneck, which is the thermodynamics of reading and writing from memory. So all the physics of computation of the kind that you're talking about would speak to the most efficient way of belief updating, or the energy cost of belief updating being described by Landauer's principle. That's an idealization. The actuality is you spend 99.9% of the energy reading and writing from memory. So the agenda of thermodynamic computing is to do in memory or in process or substrate dependent computation, so you don't have to read and write from memory, and thereby elude the von Neumann bottleneck or the memory wall, so you can actually get to the Landauer limit via the Gininsky equality, so that you don't need a nuclear power station to power your computing. You can do it with a battery. Yeah, that's the ultimate agenda that people will be chasing in the next 5 to 10 years once the current AI bubble has burst. So this paper just takes you through these arguments, but there was something particular. There's a particular reason I put this up, and I'm just trying to recall what it was. The stochastic, the versus statistical. Oh yeah, it was the information geometry, and you clearly had a sufficient fluency to respond to the question about the information geometry. I think the notion of information geometry is going to be quite central in the way that you tell your story at some point. And you'll see why later on. So in an information geometry, you're basically working on a manifold where every point corresponds to a probability distribution or a belief. So this is where information theory gets into physics through an information geometry. And the metric on these spaces is your Fisher information metric, also called the information length, and the efficiency of information processing is the information rate. It's how far you move on this statistical manifold per unit time, and you want to make that as efficient as possible. And the from the point of view of the free energy principle, then this manifold supports a free energy functional that you are always trying to minimize. And this plays a role as of a potential or a Lagrangian of the kind you were talking. And the path independent energy or difference between the free energy before and after attaining your moving minima um, it corresponds to the thermodynamic um, work required to update your belief by moving on that information manifold. The reason I'm going into that is because of your focus and mention of gauge theories and what seemed to me sort of the heart of this resource reallocation, which in my world would be basically an attentional resource. Um, and do I attend to this or do I attend to that? I can't attend to both at the same time. So computation in terms of the belief updating or self-organization on a statistical manifold, what does that look like? The key thing here, which I don't think you sort of drill down on, but I'd be interested to hear after you've done a bit of reading your thoughts on this. The key link between attentional allocation, resource allocation in cognitive neuroscience and the thermodynamics of computation that you're talking about is that you can read the attention as assigning a certain precision to various belief structures. Why is that important? Well, the precision or the negentropy of certain belief structures corresponds to the Fisher information metric that determines the information rate. So if you wanted a gauge theoretic formulation of your ideas, it is likely that you will end up um, observing that the key metric that determines the efficiency of belief updating as scored by the information rate, which is the information distance divided by per unit clock time or universal time, rests upon the information distance. And the information distance is a path integral of the curvature or the precision of the free energy landscape. That just is the mathematical homologue of attention. And for your interest, that is also mathematically the same thing as the Kalman gain and the Kalman filter, for example. It's basically how much um, precision or weight do I allocate to this source of information, or in Bayesian statistics or Kalman filtering, this prior belief. And it strikes me that if you could tell your story, sort of resource allocation for the psychological reader, you can read this as an allocation of attention. If you were a physicist, you can read this as an appropriate allocation or navigation of of a Fisher information of the curvature of your information geometry as you are now doing your belief updating on this information geometry. So I repeat that this paper sort of takes you through the background, sort of the minimum you need to know about information geometry in order to make that link, and then unpack it later. So that's why I put that up. So other things I thought you might be interested. This is just for fun, but certainly there is an active inference way of scoring the amount of cognitive effort, which is to a certain extent related to the energetic the differences in the Lagrangian or the path independent action scored by the differences in the potential before and after moving. But in this instance, it's not moving in belief updating, but it's moving whilst planning. So you can sort of think about the effort it takes to execute a plan or at least the anticipated effort is scored by the amount to which my beliefs move on a statistical manifold. That can be measured in terms of a Cahill divergence or indeed an information length. So this is a work by Thomas Pardis trying to drill down on what people think what people mean in cognitive neuroscience when they talk about effort that may or may not have a close relationship to the efficiency and the and the imperatives that you were using, E sub A, the allocation aspects that you were talking about. Um, yeah, why have I put this up? This is a game by Thomas Parr, but I thought you might be particularly interested in this in terms of. Oh yes, it was just a pure active inference-free energy formulation of the something not dissimilar to the paradigm that you were introducing when talking about your empirical work with the functional connectivity and the like. It was just simulating um, um, various decision-making tasks where you have this problem of allocating resource. I can't remember whether this is specifically attention. Sometimes this resource allocation can be cast as a sort of internal resource allocation in terms of attending to this or attending to that or directing your attention to this as opposed to that. Or it could be overt in the way that we actually sample the visual world with our eyes. We can't see everything all at once. So
Right.
we have to allocate that allocate our oculomotor machinery and saccadic eye movements in a way that maximizes the precision effectively, reduces uncertainty in the right kind of way. So there's interesting maths that you may or may not be able to either heuristically or explicitly and formally link to the epsilon, the term pre-multiplied by epsilon. Um, um, you know, and this works with discrete state space models, and it's explicitly active inference based, but it does deal with the similar kinds of problems that you were exploring and in your empirical studies. Yeah, you talked about Lagrangians, and I thought that was exactly the right way to go. You also talked about a path-integral formulation. So this is a more recent formulation of the free energy principle, using explicitly a path-integral formulation whereby working in generalized coordinates of motion, not just generalized coordinates, but generalized coordinates of motion, you can treat the Lagrangian in generalized coordinates of motion as the action and then derive the free energy and the expected free energy, have the functional form that you indicated, but also have a functional form that was very closely related to some of your other expressions. And my hope is you can sort of pick out which of your expressions had the closest association with these temperature-free formulations. So there's no temperature in the free energy principle. The temperature gets into the game in terms of, again, it's another precision or negative variance or inverse amplitude of randomness, usually in the form of the precision of prior beliefs. So whenever you read temperature in a thermodynamic context, I read um, um, inverse precision as actually another statistic that that engenders another information geometry that has implications for the curvature of the original information geometry. So I thought you might like this just to show where the variation of free energy comes from. It just comes from first principles, density dynamics, and we'll have suitable references should you want to pursue that. This is a very early paper that you may or may not want to read. It was didactic. It was written for neuroscientists or at least biologists by somebody who had your mathematical or physics skills and fluency. And it just tells a story, which I've just told you, which is that if we limit ourselves to understanding self-organization in terms of movement on a statistical manifold or an information geometry in an information geometry, the most important thing at the end of the day is the metrics that define that geometry, and that metric just is the curvature of your objective functions, your energy functions, and that translates in the curvature translates into precision. So, if you've got a statistical manifold and you've got a very, very sort of sharp value with high curvature, implicitly, if you move your sufficient statistics on that manifold, your beliefs are changing very, very quickly. you're moving through lots and lots of different kinds of belief structures, so that your information rate is very high, and of course that will induce a high thermodynamic cost via the Janinski equality, or through Landauer's through the Landauer bound. I repeat, this is quite an early and it's somewhat heuristic, but it will at least allow you to, when you mention gauge theory, nod to other attempts to cast the essence of belief updating in information geometries um, um, as a gauge theory, and allow you to highlight precision and attention that has to be allocated in the right kind of way. Speaking to your
And I think something like this would be really useful to kind of reference to if I want to go for a physics of life review, to be able to, again, as a review, maybe this would be a good paper to look at. That makes a lot of sense to me.
Good, yes, yeah. I'd say don't expect too much from it. It's not very mathematical, but at least it's concept, as you say, it's a nice conceptual pointer to a branch of you know, one way of formulating probability theory and information theory and their attendant geometries. Another interesting one, I noticed you using efficiency and degeneracy towards the end of the paper, and I think quite rightly associated the degeneracy with the entropy part, certainly of the variational free energy, or the kind of entropy implied by James's maximum entropy principle. That's just made explicit in this sort of cognitive neuroscience paper that calls upon the free energy principle just to try and formalize the notion of degeneracy. And again, it's something that you can just nod to or refer to as a vindication of the somewhat paradoxical, because the way that you express it in your presentation was, that the degeneracy was proportional to TS, the entropy, and under free energy minimization, that would entail a maximization of the entropy and a maximization of degeneracy, which is interesting because a lot of people think the degeneracy is bad. In fact, it's very good. It provides a certain robustness, certainly in a genomics context. What is bad is the redundancy. That's something else. That's a complexity term in statistics. So I think I like that bit, and I think you should sort of just spend a bit of time unpacking why degeneracy is good. And of course, if you unpack that at the end of the day, you can say, and all we are talking about is James's maximum entropy principle. If we associate entropy with, or TS with degeneracy, and of course the inverse redundancy is efficiency. So there is another side to the coin. You can rearrange it, and that redundancy or inverse efficiency, read in terms of complexity, is another interesting point you can make, because the complexity under the free energy principle, or more generally statistics, is just the KL divergence between your prior and your posterior. So it's literally how far you have moved in terms of a relative entropy when you do belief updating. And you want to try and minimize that whilst maximizing the entropy. So you want to minimize the degree to which you've moved, minimize your information rate, because it is costly, via Landauer's principle and the Janinski equality. So it all hangs together very, very nicely. If you can join all those dots in a way that the reader, the reader will have access to and understand. You mentioned sleep and on a number of occasions. And I was smiling when you did that, because again, that notion of being the most efficient as minimizing the degree of belief updating by minimizing the information length, or the potential difference between your prior and your posterior on a statistical manifold, is exactly what underlies interpretations of sleep from the point of view of Geoffrey Hinton's wake-sleep algorithm. So this paper is written for neurobiologists, and it's about neurobiology, but its basic message is very similar to what you were intimating, that you can optimize and render more efficient your engagement with the world from the point of view of the free energy principle, your generative model, by minimizing that complexity. And you can do that without data, because the complexity is just a function of your posterior and your prior. It's not a function of the data. So it's something you can do while you're asleep. You can do all your pruning, and that also can be read as synaptic homeostasis. And you mentioned sort of the synaptic mechanisms and homeostasis possibly separately, but you can understand this very much in the spirit of maximizing the efficiency by minimizing the complexity of your implicit generative models just by, again, this is a slightly different kind of allocation, but it does speak to the potential importance of understanding everything in the context of this information geometry and how you move through this geometry as you live. What's this one? Oh, and that was just a really
Interesting you brought that up with the sleep in consciousness. This might be from my thinking about that specific topic. I think awareness and in consciousness is exactly the same underlying phenomenon. Like if you try to separate anytime you use the word consciousness, you can I don't think with any exception you can replace it with awareness and it doesn't change the meaning at all.
Yes, yeah. None of what I've said it touches on deep issues of awareness and consciousness. But of course, you're right. From the point of view of sleep, yes, you are not now. You have a different kind of consciousness. Yeah, you could argue, and Alan Hobson did indeed argue that having dreaming is just another state of consciousness. So there is a kind of awareness going on. It's just not about the outside world. It's
exactly. I think it points to the exact same underlying phenomenon. Like consciousness and awareness, I think exactly the same thing.
Yes. Although don't mention that in your physics of life review. All right.
Yeah, I'm not. No, that's between us.
Right. You can forget about this paper. It's a very old example. Yes, it was when you were talking about sort of synaptic. I can't remember what it was, but certainly you were talking about one point about sort of pruning and homeostasis, and in the context, I may be misremembering or minimizing redundancy, and certainly that can be construed as a process of a slow process of free energy minimization through removing redundant, inefficient parts of your model at the synaptic level just by pruning various synaptic specializations. So this is a very early neurobiological example of that, which you can probably forget about. That's exhausted my.
Well, thank you so much. This has been highly informative. I've learned much more than that. I mean, I feel a lot more prepared for the next steps, whatever that may be now after all of this. So thank you so much for taking the time to hear me out here and your feedback. I do, and everyone here, of course. And thank you for everyone. This has been a tremendous opportunity, and I feel honored to be here and present this to you all. So thank you.
Oh, thank you for saying that. And I repeat, feel welcome to come back until you feel ready to submit your physics of life review or computational psychiatry paper.
When I am ready, should I just send you like a message in the chat here to let you know?
Well, yeah. When you're ready, contact the chairs, and then they will discuss a potential session of this kind, just so you can take us through the skeleton of your paper and possibly the figures.
Sounds like a plan.
Yeah.
Wonderful. Thank you so much.
Totally.
Yeah, as Carl said, just feel free to email us again and we can reschedule a new session for you.
Yeah, once I'm closer to getting towards a real paper ready to go, I'll let you guys.
Yeah, no rush. Take your time. Yeah. Thank you so much, Kyle. And thank you, Carl, as always. Yeah, let's give a round of applause to Kyle. Thank you so much for your presentation, and hope to see you soon again around here.
Sounds good. I'll be around for if nothing else to attend some of these talks. Very interesting topics you guys talk about here, so I'm happy to be around.
Perfect. Thank you.
Thank
See
you
you,
all.
everyone.
Bye-bye.